maybe I'll rename the slide later when I save this slide deck again. Maybe it's novel knowledge within neural networks or something like that. So I'm not sure really what the theme was of the three readings that we're talking about today, but there are several things that I wanted you guys to be aware of, that they're all techniques that you could use in a paper. I've seen people use these techniques in a paper. And so as you guys are, developing your ideas, and you're looking for what other way can we triangulate our experiments or get a little bit more insight of what's going on. I just want to give you some exposure to some other things that people do. So this is so that if you can't tell, like the whole class has been this. We're only scratching the surface of many of the things that people do in interpretability research. But I'm trying to bias it towards things that I've seen like show up in a bunch of research papers that as techniques that people reuse. Okay, that's great. Okay, so the first thing is training dynamics. So you guys are all studying pre-trained networks that have capabilities, but those capabilities didn't materialize instantly, right? All these networks were trained over some procedure. This class is not about the training process, but it can be interesting when you're looking at the internal circuits, the internal beliefs of the model, to see how those processing pathways evolved over time. And sometimes the story can be very interesting. And so one of the early papers to look at this was a paper called grokking. And so there's a few grokking papers, and there's one that I assigned you guys, but then this is the paper that came before that one. Did anybody look up this one? This one is from Power et al. Anybody look back on that one? That's great. I think this is a good thing to do. The paper I assigned you was like a follow-up paper, and it might be easier to understand if you like skim this one. So I'll show you what the original paper was. It's relatively simple. The idea is that they're going to train a toy language model, and they're going to train it on a really simple language, which just has lots of sentences that look like this. A plus B equals C, or not plus, just arbitrary operation. A operated on B equals C. For lots of different letters, A, B, and C, just mixed up, but always true statements. And what they do is, to get their true statements, they form these little multiplication tables. And then they fill in the multiplication tables according to some math operation, like addition mod 5, or division mod 5, or something like this. And then they pluck out a few of these, some percentage of these. They might pluck out half of the entries in the multiplication table, and they say, they're not included as part of the training set. The rest of them are included part of the training set, and then they just train the model on sentences that sample from this multiplication table, and they see how does it do. And now, because they've held out some of the facts, they have two measurements they can make. They can measure how well does it do at remembering the ones that we've included in the training data. And they can also ask how well does it do on the things that we haven't included in the training data. And, I think the people who did this, they didn't really have any idea whether the neural networks would actually guess correctly the things that they had never shown. And actually, when they first train them, they do really well on the facts that you show them, but then the accuracy on the facts that you don't show them is stuck at 0. So, it sort of suggests the neural networks, what?
Memorizing it rather than...
That's what they call it. So in machine learning, and so anybody who's taken a machine learning class will know, this is what we call memorization as opposed to generalization. It means that it can regurgitate the things that you expose it to in training, but it can't figure out anything that extrapolates beyond those examples. It basically is 0. So that's sort of where this experiment sat for a little while until the mathematicians who tried this, for whatever reason, they just let the computer run longer. And after they ran it for 10, 100, 1,000 times longer, they just started to see that the holdout started to improve. Now, who here is taking like, machine learning class, right? Yeah, like all the computer scientists. So, have you ever heard of different regularization methods? Have you heard of the regularization method, early stopping? So, what is regularization supposed to do? Is it supposed to hurt or help with generalization? It's supposed to help generalization. And so, the intuition is if you like, how would you like get better generalization? By training longer or by stopping early? Stopping early. That's like what they teach you in machine learning class. So did these guys stop early?
No.
Yeah, they only trained like 1,000 times longer. What the heck? This is the opposite of stopping early. And then what happened? Like it generalized anyway. So because it's so counterintuitive, right? Because it's not what they teach you in, machine learning class. There's a little workshop paper and a little tiny workshop at, I forget, ICML or something. And it just like had this little observation of this little toy thing with this 1,000-fold increase in training time, and then so that a nice jump up in generalization after this. Even though it was this humble little workshop paper, it got lots of attention. People were like, "What the heck is happening with this?" Right? That makes sense because it's like it was an example of something counterintuitive going on, and it's systematic. So it's not just one run; they ran hundreds of runs and so on, and they found this systematic effect that they plotted out and quantified in different ways. So that was the original paper. Out to give you a little so that they see the subset is learned instantly. The unseen facts are guessed a lot later. They had some patterns that they said the more emissions, the longer it takes to grok. So this is the memorization cliff. This is the grokking cliff. They call this grokking. So they gave this a name. When you train a long time, then all of a sudden the network learns something. They call it grokking, and because are people familiar with that English word? It's kind of a California word. Yeah. So, but it means like, oh, I get it now. I grok it. It's not like something that people would say after they meditated a long time or something. Meditate on this and grok it. Okay. And so here's like an example of an extreme grokking holdout. So they were very proud to put this in the appendix. We're taking a look at it. So this is a multiplication table. It's so huge that they've had to use all the Hebrew letters and all the Greek letters because they ran out of like English letters to put on each one of the things. And so you multiply one of these by one of these, and then you get some other letter in the middle. If you zoom in, you can actually read these letters. And you can see that all the blank ones are ones that are not included in the training data. And they say, this is an example of a multiplication table that groks. We give the network like all these questions as training data, and then after we train it for 1,000 times longer than you normally train it, it correctly guesses all the others. It's kind of amazing, right? Like the extent to which it guesses correct. What the heck? So that's where this other paper comes in. So Neil Nanda and collaborators in the California crew here, they tore open one of the transformers to see what was going on inside. And what they said is, oh, it looks like after you train it for a long time, when it grows, it develops a very funny representation. And they say it goes through phases. Well, I don't have the phase diagram here. Maybe I have it later. Where early on it uses one strategy, and then later on it develops the second strategy. And the second strategy looks like this. In the second strategy, so who understood or who didn't understand this analysis? I'm not sure it was like super well explained in this paper. So when Neil says, "Oh, I see these Fourier components in my neural representation," does that make sense? See, like what the heck that is? I can make it concrete. wants me to make it concrete? Yeah. All right. So let's take like the embeddings, for example. So when you feed in numbers into their neural network, then they come in as vectors. So I don't remember what dimensionality they give, but they might be, oh, it looks like 50. Well, I can't tell. Um, I'm not, maybe not, it's not 50. So, but there might be 1,000-dimensional vectors or something like that, or it might be 100-dimensional vectors. Doesn't really matter, right? So, but they have some embedding dimension that they use to represent every input thing. But now, what is the input vocabulary for this A times B equals C thing? Well, they're encoding modulo 113 arithmetic. So they need 113 letters for one for each one of the numbers, right? And so, they have they're embedding a matrix is a lookup table with 113 vectors, one for each letter. So if you say A, then that's a vector. If you say B, that's another vector. If you say C, that's another vector. And so now it's in practice, they're learning modular arithmetic. So A is actually 1, and B is actually 2, and C is actually 3, right? And so if you take your 100-dimensional embedding vector and you line it up so that all 113 numbers are in this big grid, then what you'll find is this interesting thing that if you take different rows of the embedding vector, let's take like neuron number 5 or something like this, and then you trace, I wonder if neuron number 5 is high or low or medium for 1, and you can like plot it. And then, I wonder if that same neuron is high or low or medium for 2 and plot it. And then high or low or medium for 3 and plot it. And so you just take like a single neuron from your embedding matrix and you plot it all the way across all 113 numbers, and you'll get some waveform. Make sense? Right? So that's the waveform that they're doing Fourier analysis on. Right? And so they have a lot of these waveforms. So basically one for every neuron, or there's other ways of analyzing set of bases. But basically the easy way to think about it is you've got a waveform for every neuron. And so when you do this in practice and you look at the waveforms you get for all the embeddings, at first when it's memorizing, the waveforms look really jaggedy, just like noise, like all over the place, right? And if you would do a Fourier analysis on it, it like has all the frequencies. It's just all mixed up. It's like white noise, right? For basically every neuron. And they didn't picture this in the paper. I think that would have been useful to do. But that's what happens in practice. There's a little backstory here, which is I was also looking at grokking at the same time that Neil did. He gave me a call and he says, I heard that you're looking at this. And what's going on? And I shared with him like what I've gotten. And then he's like, oh, you're almost done with this. I better submit mine first so I don't get screwed up. And so yeah, I never published mine. Anyway.
More for scooping?
He gave me an acknowledgement in the paper saying, thank you for the informative discussions.
Wait, that's crazy. That's crazy.
Anyway, it's all right. But there's a reason I know like a bunch of this stuff here because just looking at it. So for me it's not a big deal. It wasn't a huge deal paper. I was looking on Rome at the time, which is a bigger deal for me. And so but this but yes, it's not this all on video, doesn't it? So, but Neil's incredibly effective in the community, so it's fine. But so the thing that happens is you get this crazy waveform during the memorization, and then all of a sudden when it grokks, it's like all the different frequencies they drop out, and then it's like, like white noise, and then all of a sudden it's like, the rings like this clean sine wave signal. A few frequencies like pop out, and this is what Neil is depicting here. That makes sense. And so that's what happens. It happens in the so this he's plotting the embeddings, and I don't know the total details. Oh, and I think this is the unembedding matrix. So he's plotting the unembedding. So like when it has to output the next thing, there's an unembedding matrix, and they both show the frequencies, and actually they both ring at the same frequencies. It's kind of cool. Isn't that weird? So now do you get it? Now do you see what's going on? Right? Does that make it more concrete? Okay. And so, so that's what happens. And and then he says, are these frequencies like important? Like it's like ringing at this frequency. So it could be two things. It could be that everything else is important and the frequencies are like sign of some noise, right? Or maybe the frequencies are important and everything else is like some noise. So there seems to be this clear distinction between these two things. And so he did this very nice experiment where he said, what if I like filter out these embeddings or whatever, or what if I filter out the other frequencies that are not the ringing ones? How does that impact the accuracy of the network? And it impacts it very little. I think there's a logarithmic scale, right? And then if he says, oh, what's the impact if I cut out one of the ringing frequencies, and it has a much bigger effect. This is his evidence that it's the ringing frequencies that are actually carrying the information of how to solve the thing. And so in the paper, they talk about the sine and cosine functions of like what's being implemented in practice. I won't talk about that. But basically, if you want to do modular arithmetic, you can implement it by adding together some sines and cosines, which is what looks like what these networks are doing by representing everything as sines and cosines with these clean frequencies. But the thing that's relevant so none of you are studying something where you'll see sines and cosines most likely, although maybe some of the math people or spatial people, depending on what you're doing. In which case, you should understand that. But one of the things that you saw, and you could see this too, if you look at your training dynamics, is that you'll see these weird cliffs of behavior. So here he had his insight after he found his mechanism. So for him, his mechanism was this Fourier analysis of what's going on. He did this nice thing, which he did his Fourier analysis based experiment over time while the model was training. And I think that he had what he did was he says, oh, I've got this piece of code that will tell me what the impact is if I filter out a frequency. I can either filter out the included frequencies or the excluded frequencies. And so I can make a different loss curve to see like what is the effect if I filter them out early during memorization or late during generalization or in the in-between phase, right? And so that's what these turquoise lines are, right? So the turquoise line is if I take the important frequencies, like the ringing frequencies, and I go back and I filter them out during memorization, low loss is good here. Low loss means it's like, doing pretty well. And during memorization, if you don't do any of the filtering, the memorization looks like this for the training data. And so what they do here is they say, oh, actually, it actually kind of does pretty well here, even if you cut out the special frequencies. It does a little worse, right? Because obviously, like we're perturbing the network, but it's not so bad. Like the loss is still dropping, and so that makes sense because like the special frequencies are just like 10% of the frequencies of the network, right? So this is like a 10% intervention. We're like making it. We're hitting 10% of the information there. It's not so bad, right? The network still gets better, but then there's this sudden reversal at this point, where if you cut those frequencies out, the regular training continues to get better a little bit, but all of a sudden there's this reversal. We're cutting those frequencies out makes something worse a lot, right? And so So this is pretty direct evidence that the model is starting to focus on those frequencies, right? It's starting to really depend on them. And then by the time you get to this part, if you cut out the frequencies, then basically the network can't solve the problem. Right? The loss is like as bad as it ever gets. That makes sense? And so, and then he has an inverse thing here, where if you look at all the other frequencies and you cut them out, the network can't do the task at all with the other frequencies. So what are the other frequencies? The other frequencies are like his fingerprint, his hypothesis of what memorization is doing. Is that memorization is using this mishmash of all the other frequencies, right? And so when you cut out the memorization frequencies, the network can't perform at all while it's memorizing. And it's depending on this memorization all the way up to this point until all of a sudden it's not depending on the memorization anymore. And if you cut out, actually, this is he mentions this in the sentence. If you cut out the non-ringing frequencies, then actually it starts having lower loss than the regular training. It actually cleans up the network. Oh, let me zero this noise out for you. Interesting.
These are all of the noise frequencies.
Yeah, he does it all at once. Yeah, he does it all at once, I think. Yeah, that's right. And if I read the paper right. Yeah. So it's a nice experiment. Yeah, so this is creative. This is something that I never ran myself. It's very nice to do this. And then he also shows this interesting effect when you just look at the norms of the weights, and the norms of the weights sort of have these funny little cliffs where something happens here. So even if you don't know what the detailed dynamics of your circuits are, if you just look at some aggregate data like the norms of the weights or something, sometimes you'll see them go through different bumps and things. And what this is suggestive of is, actually, at each one of these bumps, maybe the network is like learning some different solution to the problem. So I think there were some questions here about so I'm going to pause for a moment. You, Claire, Isaac, Avery had a bunch of questions that were sort of related to this presentation. So I'll let people ask any questions they had. Isaac's always a good question. Yeah, sure. What's your question?
I was thinking about this is slightly different than what I asked, but
sure.
Do you have any sense of things that do grok versus what doesn't grok? It seemed like this was dependent on finding the pattern at a later stage, kind of reversing out and how it learned that.
Yeah.
And I was wondering about the kind of in the other direction, if you didn't know the kind of stage, you have kind of predictions of, and this relates a little bit to some of the questions about causality versus correlation, where sometimes in our experiments we found there's information there that the models don't use.
Yeah. This paper got a lot of attention, and people, this graph here, right, got a lot of attention. And people notice certain things about it. And so I'll point out to you things that, circulated in the community afterward, like the skepticism. It's like, oh, wow, look at this cliff. And then later on, 1,000 times later, right, it's like, oh, there's another cliff. It's amazing. Well, this is a logarithmic scale. And this one is a little more gentle than this one. And so actually, this is a cliff, sure. It memorizes quickly. But if you were to put this on a linear scale, actually, this was very, 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 very steady, slow. It took a while for it to grok, right? You know what I mean? And so is that is grokking? Is it they have this very nice term that they use? Oh, grokking! Suddenly we get it, right? But actually, it's not that sudden a process in real life, and maybe maybe not that distinct from the rest of what's going on here. So other people said, hey, they're measuring accuracy here, right? And it's accuracy. But actually, if you measure loss, then you don't see such a cliff. Loss is more gradual, and so there was a bunch of different people who objected to the title of the paper, grokking, which is a common tension in our field because we like to pick flashy titles. I'm guilty of this, and but so the mental model you should have, the more realistic model, is this kind of phenomenon is fairly widespread. where you have different types of solutions being learned at different rates. But this idea that there's different cliffs that happen is a little bit more controversial. Some people say that there are cliffs, but they don't think that they're like scheduled, like the cliff doesn't always happen at the same time. Like the rate of discovering a difficult solution is a little bit random. Oh, actually, you see the randomness here, right? So there's all this stochasticity of how long it takes to learn this other solution. Every one of these dots, let's see, I guess this is the number of steps to getting to grokking. And this is another log scale. So it could be like 10 or 100 times more steps or fewer steps randomly. And so, so the rate of finding these solutions is sort of random. And then the idea that it's a cliff is also, people think that it's a little bit more of a slope than the way they present it in the paper. But besides like arithmetic, I think that I'll show you some other examples where this kind of type of thing has come. That'll be on our future slide. Any other questions? Yes.
I have a follow-up. So just could you go back to the slide?
Oh, this one. Sorry. Yes.
Like grok faster with less powder. I was thinking like, because they only have like 113 times 113 pairs of inputs, and like they're training on like 30% of them. I'm wondering like on this like small data set, it might like grokking happens like could it be because like it's much easier for the model to memorize, and then like later it like grokking happens because it's trying to like definitely like decrease like learning some real things, but like in reality LLMs we have like enormous retraining corpus, and like I don't know if like it's possible to like memorize all of them,
Right.
and I'm just thinking like, could the amount of training data or like could that be also affected with grok?
Yeah. Is this like a special thing about small training data? You might be right. So one of the things that is controversial here is that he's trying to infer something about deep learning in general out of a toy setting with a really small training set, and so some people think that that's nonsense. That it's very different from the organic. So this question you're asking, you're asking the question in an open-minded way. Some people ask the question in a very critical way, right? Where they say, yeah, you didn't test on big data. It doesn't have the properties that real training has. I think that's a reasonable question. I think that's also open for debate. There's definitely a community out there who thinks that the only way to really understand simple systems is to simplify them down. They say that they've done this in physics forever, right? And it did well in physics. Understand waves in a box or something like that. It helps you understand waves in the real world. But other people say that no, complexity is an inherent part of what's going on, and if you take away complexity, then you get different dynamics. So I don't have a strong belief one way or the other. Like I just keep that skepticism in mind when I read these papers and when I advance an argument like that. Make sense? Yeah, I think the jury's still out. It's all too new. We don't have a consensus. There's a question. Somebody asked a question about L2. Who asked the L2 question? That was an interesting one for this plot. Was it Hayu or somebody? So I'm going to pause. Let somebody ask the L2 question. L2 regularization, anybody? I don't remember who asked. So this is interesting, right? The weights are getting smaller, right? And they suddenly drop down when you get this different thing. And so they call this, so Neil calls this phase the cleanup phase. Right. I also saw this when I experimented with the system. And my intuition for what's going on here is this interaction with L2 regularization. And I try to convey this intuition when we teach machine learning. L2 regularization is pressure that you put on your model to make all the weights smaller. Right? So it's a pressure to make, like, try to zero out your model as much as you can. But it's just like some pressure. And your model has this other pressure, which is like to solve the problem. And to solve the problem, you can't set all the weights to zero, right? It's not going to do well, right? So to solve the problem, it has this positive pressure on the weights. It's like there's all these like computations it has to do. And to do the computations accurately, the numbers can't be zero. They've got to have some positive values. And so what you see here is that early on in training, right, memorization like blasts the weights big because like, oh, and maybe they start down here and then boom, as soon as you start training, like the weights get much bigger. And so memorization is this solution to the problem that requires you put a lot of information in the weights, which means that a lot of the numbers have to be really big, right? And then as it figures out, how to memorize a little better, like it starts to organize its information in some ways, and then the weights get smaller for a bit. And then as it realizes that a really good way of organizing the things is to use these few frequencies, it lets the model like shrink the weights further until it gets to the point where it says, oh, you know what? These frequencies are working so well, I don't need anything else. All I need is these frequencies, right? And then the optimizer says, oh, I don't have any optimization pressure on this on this memorization path anymore. I can set all those weights to zero, and it doesn't impact my loss because the ringing weights, the T frequencies, are solving the whole problem. So the L2. So that the way I think of it is like the L2 regularizer is coming through and sort of sweeping up, the old solution and zeroing it out. And that's the way I interpret, this plot. That makes sense. Anyway, a little bit of intuition, a little storytelling. Okay. That's sort of how I think it. Okay. So, Jasmine, are you online?
Yeah, sorry, my voice is still kind
Yeah,
of.
how you doing? You feel like a question?
I don't remember what I wrote. Sorry.
Yeah, so I think that you asked this question. I just took a slide here. So it's a very related question to what Isaac asked, which is like, oh, does grokking happen anywhere else? So I don't remember if you remember from the induction edits paper, but they talked about this cliff in the loss that you get when you train text, and measure it on the copying task. And then, it does well up to a certain point, and then all of a sudden it does much better until it's almost perfect. And so these cliffs, and the cliffs only happen if you configure the network the wrong way. If you don't have enough layers, it can't do it. But if you have enough layers, it can do it. And so the answer is yes. Grokking happens. These cliffs, these phase transitions, they happen in other settings, and this is like the clearest one. Here's another one. So this is a paper that my student Eric Todd just got into. I think he's going to present it at ICLR, and here he's pulled apart not one mechanism. He's pulled apart like 8 mechanisms inside this network. And then one of the things that he did is he went inside to look at the training dynamics for how these mechanisms did over a bunch of different training runs. And so this is averaged over a dozen training runs or something like that of the model. You can see that pretty consistently you have these different cliffs where different mechanisms all of a sudden get really good accuracy. Yes.
Have they tried like if I grok it on like only one particular type of data and does it generalize to other? For example, if I only do it on physics, does it generalize to like chemistry or biology?
Yes, exactly. That's exactly what's being done here. So let me tell you 2 like things that you can do to try to get grokking curves out of your papers if you want to do it. So one thing, and this is the thing that's probably practical for what you're doing, which is you have some general distribution of what's going on, and you think that you understand how a sub-distribution works. Like maybe there's like 4 different strategies that your network is using to solve the problem of estimating uncertainty or something like that. And depending on the sentence or depending on the keywords or something like that, it uses one of these different strategies. So what you could do is you could say, let's pick a sub data set of my overall data set, which isolates this strategy. Like now that I have some understanding of what it's doing, 10% of my sentences use this strategy and they exclude all the other strategies. Like it's just purely this one. Once you have that, then it's pretty interesting, not just to measure it at the final checkpoint, the final model that you're testing, but to go back into the early checkpoints if you have them, and then plot like, well, what was the performance on this little subset of data? And that's basically what this is. So basically, Eric says, oh, I'm solving a harder form of algebra problem. So he went back to the grokking paper. So he's solving problems, and he's asking, which of these problems is solved by copying? Which of these problems are solved by identifying the identity? A times B equals A, that means B is identity, right, which is a strategy. Which of these things is solved by identifying commutative inverses, maybe A times B sometimes equals B times A, depending on what situation you're in. Which things work by associativity? Which things work by cancellation? Like, can you solve it like a Sudoku puzzle, right? Canceling things out, right? And so he found like mechanisms for doing all these different things inside the network. And then he says, look, number 3 is identity. Actually, the performance of the identity goes pretty well until it drops. And it's really bad at the identity while it's learning how to do commutative copying. But then after it learns how to do commutative copying, the performance on the identity comes back and it goes near to 100%, right? And so on. So you see these funny, weird looking grokking curves. Yeah, that makes sense. So that's probably the main thing that you want to do. If you want to measure grokking, but I need to mention this other paper here. This is from who latent space models of trained dynamics. So the other thing you can do is this. So I mentioned, you can see these phase transitions if you just measure like the size of the weights, right? And if you just measure other random stuff about your network, you can just take a linear algebra textbook or something. Like how about the spectral norm of all the matrices? How about the trace? How about the maximum of all the weights instead of the average of all the weights? How about like the magnitude of the gradient if we pass gradient over the network? How about this? You can measure different things. And if you measure each one of these during all the checkpoints, you'll also see that sometimes there's like cliffs up and down, all around, right? And it's like not just a smooth progression. And so what they did in this paper, what Wu did in this paper is they said, I don't know what we should measure. Let's measure 13 of these things, right? Or some number, right? So let's take a dozen of these numbers. And then every one of these checkpoints, we have a measure. It gives us these like 13 line plots that look like this, right? All over the place. And then they said, so what does it tell us? And then what they did is they ended up training a hidden Markov model on top of this like 13-dimensional line plot, saying that, okay, if this is high, this is low, and this is medium, and this is high, this is low, right? Like all these numbers, that means that we're in state X. And when you're in state X, then you have some probability of going to state Y where this other number is high and this other number is low and this right. That makes sense? And they said, and then they did like thousands of like, training runs of some networks. And then they said, when you're in this one state, then you have some probability of going to the next state, at every iteration. You have some probability of going to the other state. And so they did this whole beautiful analysis of like what training dynamics looks like, where like it's like this picture of crystallization, like our mixture of mechanisms is like this, and then after you train a little bit, and there's a chance that you go this way, and there's a chance to go that way. You might start crystallizing your mechanisms in one direction. You might crystallize the mechanisms in a different direction. And so they did this analysis. So this is probably beyond what you would do, but I just want you to be aware that it's another approach that people have.
Yes, here states are basically the set of those linear algebra matrices.
Yeah, so every state is, so they had like something like a dozen observable variables. The observable variables were these aggregate statistics of the network, like what's the average norm of the weights or something. And so every one of these hidden Markov states, the hidden states, corresponds to some set of physical states, and so yeah, so they're asking the question: if you sort of partition your physical states into these underlying hidden states, then what's an economical way of representing everything? Like if you said, if you discretize everything, you said, I want to just have a half dozen hidden states, then which one of the hidden states would there be, and what would the transitions be between them that would describe the training process? And so that's like a classic hidden Markov model training problem. And so they just plot all their data into that machinery, and they got these beautiful plots out for what the state transitions would be, and they look like this type of thing. It makes sense?
Yes, that makes sense.
Yes.
Next question was, did they observe grokking, and if so, could they explain grokking with this Markov chains?
Yeah. So I don't know if they use the term grokking. I don't remember the ordering, but I think this is motivated by the same thing. Is it basically when they have a transition like this, like an arrow? I think that what these arrows are for them is the equivalent of grokking. And what they would say is that grokking doesn't just happen once when you have a more complicated system. You have lots of little transitions that happen when the network, it seems like it has a different flavor. And it grokks like from here to here, and it grokks, or sometimes it grokks from here and then here to there. Right? That makes sense? Yeah. And so
Dates capture the time as well.
Yeah, so I think that the way that they're thinking of it is, you can see these 0.987. So most of it, they say that. So remember in the grokking paper, there's this big variation between how long it will take. Between sometimes it'll take a long time to grok, and sometimes it takes a fewer time, less time to grok. So you can think of that as kind of Poisson process, right? You can think of it as like, well, every time you run gradient descent for another 100 steps, there's a chance that you might stumble on the solution. But then there's also a chance that you haven't stumbled on it yet. You might have to just look longer. And that's what this represents. After some more training steps, there's a 98.7% chance that you haven't found the transition out yet. You're still stuck in state one. But then there's a small, 1% chance or whatever that you found the thing that lets you get to that state. And so that might happen fast. If you're lucky, it might take a long time. If you're not lucky, that's sort of the way they model it with this. Yeah. And so I like this. I think it's, this is still the paper I think that, had the most systematic approach to doing it. But it's still opaque. So like if you just collect all these numbers, you get this diagram, you still don't know like what's in each one of these balls, right? And you don't really know if this is like real or not. Right? It's just like kind of a way of looking at what's going on. And so for you guys, I kind of recommend this. This is a lot more transparent. Like you like each one of these lines corresponds to some mechanism, some subset of data. You know what it means, right? Now it'd be interesting if you did this analysis and you lined it up with this analysis and said, ball number one corresponds to this being high and this being low in the real data. I don't think anybody's done like a triangulating paper like that, right? Trying to relate these two methods. Make sense? All right. So, okay. That was a lot on grokking. I better go through the next one faster. Yes.
I just have a question on after we do these analysis on training dynamics, have people use the information to some more practical benefit besides just understanding what's going on, like better training dynamics or something?
It's a good question. I don't know. I'm not a training dynamics person, so I'm not in the business of defending this line of work. Naomi Safra, who is like a training dynamics, either down the street, where I think his name is at BU now. Ask her. What would be good? So I think that you might have a sense. So there's some controversies that are maybe addressed by some of the training dynamic stuff. Like some people think that it can actually be harmful to train your network for the wrong amount of time. But then there's different advice that you get. Like, don't train your network. Don't give up on your network training too early. You should train longer, right? Then it'll get better. Oh, but then some other people say, oh, no, don't train it too long. If you train it too long, then you're wasting CPU, and then eventually it actually starts getting worse, right? So this whole discussion, it has to do with train dynamics. There's also other stuff, which interacts with this in practice, which is, one of the biggest things that all the giant companies are doing is they're coming up with their mix of training data. And so there's another axis here for training dynamics, which is like, well, how does the mix of training data during the process influence all the training dynamics that we've learned? And for academia, I haven't seen a lot of training dynamics papers from that point of view. Maybe I'm missing the literature. But in industry, this is like a major question. Yes.
Maybe I don't remember the exact paper, but I remember one of the events last year.
Yes.
They were doing like generative modelings of like images, diffusion models, and they had this kind of like theoretical, like a formula basically predicting when those stages would occur as a function of how much data you had. So you could say, for this training run to be worth it, we need like this amount of data for the window of useful models to be reasonably big or addressed.
So you've heard of scaling laws, right? And so obviously training dynamics is related to scaling laws. Although scaling laws they usually look at like a small number of metrics and how good is the network in general. Whereas training dynamics, people try to cut it up with a finer tooth. Okay, we'll go through Patchscopes quickly. Patchscopes is a pretty simple idea. So there was a question from Armita. Is Armita here? Yes. What was your question?
So yeah, I wanted to see where this stands compared to our previous.
Yeah, how is it related to the other stuff?
Yeah, and when we prefer this one or
Yes, and so when you prefer things in general, I think that I'm going to give you the same answer I've given a few times, which is that you probably want to not lean on too few methods, and you want to find complementary methods once you have a hypothesis that you're advancing. So if you're writing, say, oh, I think that we figured out the recommendation of this, you'll know from your own experiment like what the strongest evidence that you are most excited by. So obviously you present that first, but then after you present that, then you have to realize that the reviewers, or any reader, will look at that evidence and say, well, that comes with caveats. Every single one of the methods that we have comes with caveats. And so you can say, well, we don't just see it that way. When you look at it this other way, then you also see something interesting. And when you look at it a third way, you also see. And so the more different ways you can see the same phenomenon, the more people will believe that you have a handle on what you found. And so I'm mostly talking about Patchscopes just to give you another tool for your basket. Now, it's a good question. How does it relate to probing, patching, or steering? I'd say that this is most related to logic lens, right? That method that we use, the first week of class just to learn how transformers work. And it's logic lens is a serious method. Like you should use logic lens to look inside your things. Sometimes it doesn't give you that much insight for logic lens, and so you might not have anything to report. But there are ways of making logic lens more powerful, and this is one of them. So I just wanted to share that with you. And so there's been a few papers that have worked on making logic lens more powerful, and they all have this type of form. So one of them came out of our lab. It was called Future Lens, and Future Lens does this. So what it does is what does logic lens do? Logic lens takes a hidden state that you want to know what's going on in that hidden state, and it decodes it to a word. or set of words, right? And it decodes it to a word by patching that state to the decoder head of the transformer. It just says, I know this is in the middle of the network, but instead of you having you process it, I'm just going to skip to the end. I want you to tell me what this decodes to right away. And then it gives you a word that you can write down. And it, sometimes it gives you some interesting insights from doing this, right? Certainly more interesting than just looking at 1,000 numbers, right? You can see what words it corresponds to, right? So what FutureLens does is this: it says, well, this vector here, it was never meant to be decoded directly in the decoder head of the transformer. It was meant to pass through a bunch of layers, which who knows what they do, right? Maybe do some transformation on it until it finally comes up with the answer. And so obviously if we just run the transformer, it'll say something. But when the problem with just running the transformer is that in a lot of contexts, when you just run the transformer, it has all this other context besides it. When you just run the transformer, it doesn't tell you just what's in this thing. It tells you what's going on everywhere. There's all this attention bringing information from everywhere. So you don't know when it finally emits something if it really has to do with this hidden state, or if it has to do with all the other information it's bringing in. So what you could do is you could pluck this out, and you could find a clean transformer that doesn't have any of the context. Right, so I don't know. Maybe there's a whole newspaper article about New York City, and then this hidden state shows up and it says New York City. So is it saying New York City because of this hidden state, or is it saying New York City because of the rest of the newspaper article? Well, one thing that we could do is we could just cut out the rest of the newspaper article, get a clean transformer with no context, and we could just jam this hidden state in, and we could say, I wonder if it says New York City, and sometimes it does. It'll say New York City anyway, which means that hidden state encodes for New York City. Now, it turns out that this usually doesn't work. If you remove all the context and you put in some hidden state in, it'll the lack of context tends to make a transformer really, really think that it's at the beginning of the document, once upon a time kind of state, right? So even though you plop in a hidden state that says, I'm encoding for you should say New York City, it'll be so overwhelmed with the other evidence that should say once upon a time, it won't say what's in the hidden state. So what FutureLens is it was a recipe for how to configure a transformer so that it tends to tell you what this token would mean. And the way it worked was, instead of having the transformer be perfectly clean with nothing coming before it, FutureLens says, we're going to come up with some fake text that we're going to put there. That instead of it being the very beginning of the document, we'll take 10, we'll get 10 words that we'll put there, and then we'll find the optimal 10 words, and that'll be just the same words for everybody. But when you put these 10 words there, the 10 words might say something like, be honest about what you're thinking right now. What you're thinking about right now is this, and then you plant the thought in the model, and then it says New York City, right? So that's what the idea of FutureLens is, and we tried prompt engineering it to come up with prompts like what I told you, and it didn't work that well. But then what we did is we did prompt optimization, where instead of putting real tokens in here, we did what's called soft token learning, which we ran an optimization process to optimize tokens to do well at this task. And that's what FutureLens is. So it's a transformer with 10 learned tokens that you seed it with that prime the transformer to tell you what it thinks the token means. That makes sense? So that's something that Koyana in my lab did a couple years ago. And there were a number of papers that did different things that were similar to this. And what Patchscopes is it's a roll-up of these methods. They're sort of surveying, what other people have done, including FutureLens. And they said, okay, well, in general, here's the state of the art of what you would want to do. And so it's a generalization of FutureLens. to do this. And so, so instead of having one fixed prompt, they suggest a bunch of interesting, clever prompts. Like, so here's a really clever prompt that I wish I thought of, which is really interesting. Is a prompt that says, cat goes to cat. 135 goes to 135. Hello goes to hello. You can have actually a really long prompt like this. Like, the same word goes to the same word. Oh, you have some word in the input, you gotta have that word in the output. The same word in the input, it's an echo. Echo, echo, echo. Say the thing that you said, say the thing you said, right? And then what you do is you put this thing in, you put a dummy token in, and then you patch in, the representation that you wonder what it means. And then you say, echo that. Right after it's seen like 100 echoes. Now it's got to do another one. And then it tends to tell you, that's Jeff Bezos. Right. So that's pretty neat. So they came up with a few different cool tricks for doing this. Another cool trick that was in Patchscopes is that instead of patching, like we were such purists on feature lines, where like if you're at layer 5, then the transformer expects to see you at layer 5. So patch into layer 5. That's where we put it. We're like, I don't know, you don't have to be such a purist. You can just stick that back at layer 1. And they just measured it, and it tends to work better. And so they had a bunch of results like this where they were just measuring, how accurately they can recover, a description of what's going on in that state, and they sort of, they tweaked it and optimized the process a bit. So if you want to do something that's like Logic Lens, but you wish it like were better or cooler or something, somehow you might read the Patchscopes paper. That makes sense? Yeah. Or you can also use Logic Lens, which is super simple, which doesn't require any configuration or anything. So this is another possibility. It's also related to patching, right? Because you patch from one model to another. So everything that you're doing for your patching experiments, it would actually be the same. The same framework. Oh, there was a question from Ananya or Yuchen. Like, what was it? Yes.
Yeah, I guess the question was like, this kind of comes with this thought process that you're basically asking the model again, hey, you thought about this before. What do you think about this again?
Yeah.
How do you trust that the model will produce like the right?
Yeah, I don't know if you can. It's a really good question. It's so I think that if you're really, really worried about deception, then going back to the model to ask again, like doesn't totally solve the problem. At least you're running the model in a way that it wasn't trained to do so, right? So so you're not overfitting on, training like if you believe that there's some way of setting up the network to be honest, like this is like an honest situation. It's like, oh, the network is just going to say what it had to say. It's an honest state of mind. Then maybe, but there's a proof of this. I think the proof is empirical. They're like, we just measure this on 1,000 things and it seems to work okay. And so hopefully with the 1,001 thing, maybe it'll work okay too. But it's not a proof. But it's just building confidence. It's just another method. I probably wouldn't use it alone. I'll use it with other things.
I have another question.
Yes.
In the case of the future lens paper, you use 2 different transformers. So even in the case of
it was the same transformer.
Oh, okay.
Yes.
So were they trained on the same? Like, if we were to change training data, or basically patch activations from a similar, like, or a different run, would it still be?
Yes. There's another paper from the Translist paper. I forgot the name of the title of the paper, but Sarah Schweitman and so on, where they do this, but they train a different transformer to look at the states. So where we have some state, and you want to like get a description of what it is and why. Why does it have to be the same transformer? It could be a very different one. Just train on the problem of understanding the states of this one. So you can do that too. That's a more intensive process. So like, why would you expect some other transformer to understand the states of this one? Well, it wouldn't. It has no reason to. So it's almost like kind of training from scratch. It's got to learn this foreign language. This one is sort of funny because you can see how this transformer would already kind of understand the internal neural language of itself. Right? So it's like less tuning that you have to do. Maybe just prompting. Right? Yeah. And so, but that's another approach. It's a very good question, and it's a very reasonable approach, and it's another one of the avenues people could take. And so, Okay, so that's Patchscopes. I like the how do we trust a model to explain its own representations questions. It's very deep. And it's like maybe one of the fundamental questions of our field. It's like one of the things that we puzzle about. So okay, so the last paper I think is the one that I think is the most important out of this, but it's the least likely that you would actually use this in your research. It's actually a fairly difficult technique to use, but I want you guys to be aware of it because I just think it's really important for this direction. And so this paper was about chess. It was about AlphaZero, which everybody knows can like beat all of us in chess. Can probably beat everybody on the planet in chess. It's like a superhuman chess player. And so whenever you have this question of what does it mean to have superhuman AI, you should remember that we already have superhuman AI. We have superhuman chess players that can beat you not just through like throwing huge amounts of compute at you. They can beat you the same way that if you go to Harvard Square and you find those chess people that sometimes hang out by the subway station with all the little chess boards on the tables there, and they tie their hands behind their back or whatever, right? And they can play like 12 chess people at the same time. They just go and they move again, and then beat everybody, right? They don't have to think about your game because they're so good at chess, they can just see the future, just looking at the board. AlphaZero works the same way, and it works better than most professional chess players. So in the paper, they have this example of I'm not a chess player. The author Lisa Shutt was a professional chess player, and Lisa looks at this board and says, obviously anybody who's like a pro chess player would move a certain way, but the weird thing about this state is that AlphaZero would move a different way. And there's many situations like this where like every human who's like trained in chess would go one way and AlphaZero does a different thing. It's like for them, this is like concrete evidence that and it beats everybody. Like that it has superhuman knowledge. It knows something about this move that people don't know. What does it know? That's the puzzle. So what is AlphaZero? It's what they call a paucity value network. Right? You can think of it. So basically, it takes a chessboard as input, and then it gives some assessment of like how good this chessboard is, right? And you can use that to search over different possible moves. Oh, if I move here, does that make this chessboard better? Does it make it worse? If I move there, does it make it better or worse? You can run this whole tree search, and that's how this network does. It basically gives you its quick assessment of how good it is. And with a very shallow search, you can just use it to pick what the best move is. You can run a deeper search too, to see like all the different possibilities out. They call it Monte Carlo tree search. So you could go 3 or 4 moves deep and generate hundreds or thousands of different different possible future boards. And then you can ask, what do you think of these boards? And then the interesting thing is the way they train this network is that after you do this whole Monte Carlo tree search, now you've got this estimate of like what the best board is, it's possible for you, what the best board for your opponent is, what they would choose. And it gives you a much more accurate view of like what the future holds because you've done the search out 5 moves ahead. And then you say, well, what was the original estimate when I just looked at the board without doing the search? And it's not quite as accurate as the estimate I get from doing this 5 deep search. So let me train it. Let me update my little quick assessment to correctly reflect like what a much deeper search would have had. Let me memorize the output of this deeper search into this network. And so that's basically how the AlphaZero style deep network training things work. You just have them play lots and lots of chess games, do lots of Monte Carlo tree search, and then try to memorize the output of Monte Carlo tree search into this policy value network. And so the question is, so when you're done, you don't even have to do the Monte Carlo tree search anymore. You can just play against the policy value network, and it can still beat you, right? Because it's like guessing how the search is going to come out, and it's usually right. And so the question is, what the heck is going on inside this policy value network? Right? Are there superhuman concepts in there? And it's weird. How do you find a superhuman concept? Like, here's my questions. Right? How do you find it? It's like you guys are looking for concepts that you can write down. Right? Like uncertainty in a network, or power relationships, or political leanings, attribution of words, spatial understanding. But for superhuman concepts, we don't know what they are. You can't guess what they are. Even if they showed it to you, you probably wouldn't recognize it. Right? We certainly don't have any words for it. You're not going to look. You're not going to find it in the library. Right? How do we even notice it's there? And then how do we learn it? What a cool question. Isn't this a cool question? Right? This is a cool question. It's such a cool question. I think it's like the most important paper in the last couple of years, this one. And it's hard to do, and they have a formula for doing it. So there's a few pieces of evidence. So first of all, they're like, does alpha zero even contain new concept? Oh, Grace, you've had this question. Ask the question.
Yeah, so they if I remember correctly, they would like take the ways that human people would play and how Alpha Zero would play,
Yeah.
and then they would do some sort of thing to find the dimensionality, like the rank
Yeah,
axis.
like that. Yes, exactly.
And
Exactly.
then they claimed that like, oh, if the rank is higher for the way that the Alpha Zero plays, then that means it has more concepts.
Yeah.
But I was curious, like that is proof that there are concepts that humans don't have, or at least not reflected in how they play.
Okay.
And so I was curious, like, 'cause it seems like with LLMs, for example, they're very deterministic in how they talk. Like, it seems like they could have access to different concepts, but have a lower rank, or just more narrow in the.
Yeah. So I think that's right. So I think that's the proof. Okay. So the question is, like, does Alpha Zero actually know something that we don't know? And so the first experiment that they did, or one of the first ones, was this one that Grace is asking about, and it's this. It's so you can feed Alpha Zero's own chess moves, and like halfway through an Alpha Zero played game, you have some chess configuration. You can feed it into the Alpha Zero thing, and you get some vector representation of the chessboard. And get near the end of the network, and you could just feed through millions and millions of these, and you get millions and millions of vectors, and the millions and millions of vectors will like make some big cloud in vector space, right? Now the interesting thing is that cloud has a different shape as the cloud that you would get if you fed in a different data set. So the cool thing about chess is there's so many human played games that are all recorded in great detail. You can just go download millions and millions of human games, and you can also feed the human games into the Alpha Zero's policy value network, and you get a different cloud of vectors, right? And so the first thing they did was they said, I wonder if these clouds are different from each other, right? And they are indeed different. So you can measure it at different layers. And so at the input layer for the network, they encode the chessboard in I guess is this what I don't know what 8,8,119 is. Okay, so I'll just say a 7,000 dimensional or 7,000 rank representation. Probably the size of it. Oh, 8 by 8. Oh, I see. 8 times 119. Yeah. So they have 119 dimensional vector for every square, and they have an 8 by 8 board. I'm such not a chess player. So that's perfect. So if you multiply these numbers, you get like 7,000. Right. So they have this 7,000 dimensional thing, and if you feed in all the inputs, then the inputs like human data. If you look at the dimensionality of this cloud of inputs, it turns out they're not using all 7,000 dimensions. It forms approximately a 730 dimensional cloud. Right. It's like pretty flat in that space. Like real chess games aren't just a random array of pieces. I think there's some structure, and this is like what the structure looks like in linear algebra terms. And actually, Alpha Zeros has a little less diversity. There's like 2 dimensions short, right? So, but about the same number, right? So, but the interesting thing is, after you have it, process it, and think about conceptually what it goes through like 19 levels of transformers or something, right? you get to the 19th layer or the 23rd layer, and then the situation inverts. Now, human data has like 7,000 dimensions out of a possible maximum of 16,000 dimensions, but the alpha zero is like a couple hundred dimensions larger, right? So I don't know what that means at all, right? It's not like a standard analysis, but it's kind of interesting. And so they said, oh, maybe this is evidence that it knows it's representing something richer. The dimensional, this counting argument at least tells us that we could find some vectors in the alpha zero representations of the representations of alpha zero games. There are some vectors that don't exist in the human games. It means that we could, if we look at this linear algebra, it gives us this ranking function, this very interesting ranking function, where you could go over all the alpha zero games and you could say, how close are you to the cloud of human games, right, according to the representation? And some things will be like pretty close to the human games, to the 7,800 dimensional thing or this, right? Some things will be pretty close, but other board states will be very non-human-like. They're the alien games. They would never show up in like human games. Right? Does that make sense?
When they analyze the human games, it's like an average of all players. Because I'm assuming I have less moves than Magnus. I don't know.
It's not average. I think that you're right. It's an aggregate of all the things. And when you're doing this dimensionality thing, there's probably some averaging effects of like how much do you count somebody, like if the same game state shows up 1,000 times, and then another game state is very rare, how do you weight it? And I don't know the details of like how they weight all the things. So it's a reasonable technical question, and we'd probably have to mail the authors to ask how they did that. But I'll just continue on telling the general story without knowing the technical details of my paper. So this is instantly interesting. Games that are not human-like, right? And so they found really three things that they needed to do to isolate interesting vectors. So they have this vector space, and now what they're after is they want to know the most interesting vectors in that vector space. And it's a 16,000 dimensional vector space, and there are 8,000 dimensions that are like being used. So how do you find like interesting 8,000 dimensional vectors? So here's what they did. They had this 3-step plan. So first of all, they made like a list of candidate concept vectors using good old-fashioned chess knowledge. So they analyzed a gazillion AlphaZero games, and they used classical techniques, probably the Monte Carlo tree search that AlphaZero was doing. They could look at the Monte Carlo tree search at every step, and they say sometimes the Monte Carlo tree search is really unambiguous. Like there's one best move, you're just going to do it. It's not a very interesting position. But sometimes Monte Carlo tree search like has like a dilemma. Like there are two paths that look pretty good. These are like the choice points in a chess game. So they went through and they just did this classical chess analysis, and they just found all the interesting choice points. Probably like millions of like interesting positions, right? And they threw out all the rest of the interesting things. They probably threw out 99%. Right? And then they said, okay, of these interesting positions, how many have humans seen before? Like how many are like emblematic of like what would show up in a human game? And so they did this linear algebra thing. They said, oh, you could project it onto the human 7,800 dimensional vector space subspace. How far do you have to go to become human-like? How far is that projection? And you could project onto the AlphaZero subspace. How far do you have to go to be on like the typical AlphaZero subspace? And then if you have to go really far to be a human, but not very far for AlphaZero, then it's very emblematic of like an AlphaZero game and not very emblematic of a human game. So they basically took the difference between these two distances, and they selected the top 1% or something like that for games that are most AlphaZero-like and least human-like, the most novel. right? And then they still had too many vectors. So they're like, we still need to throw away like 99% of our vectors. So then they had this third thing, which I thought was the most clever thing they did, which is they filled out vectors that are not learnable. What the heck is that? So for this, what they did is for every one of these vectors, they made prototype training sets for the concept. So for any given vector, they found lots of games where the AlphaZero was like, yeah, that's like a typical situation for this vector. And then they did the Monte Carlo tree search to say, in this situation, you're choosing between these not as good situations and these better situations. And they would make this training set that of like example board positions where this is like the contrast between like the good path for this concept and the bad path for this concept. So I'm conflating a couple things that they did that are very similar in the paper. So one of the things is, how did they get these vectors in the first place? They had all these board positions. How do you get the vector from a board position? Actually, what they did is they didn't just take the vector from the board position. They actually formed these contrast sets. And then after they formed the contrast sets, they would use it to create a probe for what probe at that board position would tell the difference between the good path and the bad path. That Monte Carlo tree search. So Monte Carlo tree search, it was all choosing between a couple different things. There were these choice moments. And so they would make a probe for what vector representation was a good probe for whether you went on the good path or the bad path. And that was the vector that they were interested in. And then they went and they looked for games that had this vector in its representation. And then that allowed them to find a lot of similar games with a similar situation. And then they would dump out these sets of board examples of like, these are examples of good examples of this concept and anti-examples of like missing this concept, right? And then after they had all those examples, then they would go to a chess engine, an AlphaZero chess engine, just like policy value network, and they would train it on that data set, on those like, 100,000 examples of good and bad examples of this vector. And then after they did that, they would find that if they trained it on this data set for a while, that I don't remember C and R and all the things, but basically, in blue, I think it would start doing better at the concept that you trained it on, right? But then not only did it do better at the concept you trained it on, sometimes it would do better on related concepts, on different vectors, right? And sometimes it would actually do better at general gameplay as well, right? And so what they did is, now it wouldn't happen like this all the time. Often when they chose these sort of training sets, they would put it through this procedure and the network wouldn't learn. Like these numbers wouldn't go up, right? It wouldn't get better at chess. And so in those situations, the probe vector or whatever they found was not doing a good enough job at coming up with distinct things that could be exemplified, like a lesson that could be exemplified by sharing like chessboards. And so this worked sometimes sometimes it worked badly. So they said, we're just looking for the best concepts. So again, they threw away 99%. They said they just tested this on a lot, and then they only kept the top 1% of vectors that had the best transfer. In this way, they were the easiest to distill into lessons that were learnable, right? And then finally, that gave them a handful of vectors, like a human-sized set of vectors. I don't know how many vectors. I should ask Lisa what the number was at the end. And then they took these vectors and they said, okay, now what we'll do is we'll teach them to humans. And they put them in, they printed out all these little chessboard manuals like this. And they said, according to this chess book, here's a really challenging chess puzzle. Tell me which way you would move. And then ask the humans to answer. And they know which way is the good way and the bad way. And they score the humans on this, and they give them 20 chess puzzles or something like this. And then after that, they would say, okay, so let me tell you the secret. Actually, you were wrong for most of these. This is the way it goes. But I'm going to give you a book of a dozen examples of like the good examples and the bad examples of each one of these concepts. And you can just study this book, just the same way that we trained Alpha Zeros. And then after they did that, the people would have a few hours to study. These were all like grandmasters. These were all like, it was a Google paper. So they paid these people to like come to the Google campus and hang out and have fancy food and talk about chess all day and like learn from Alpha Zero. They loved it because they actually learned these new chess techniques, and then they would come back and they would take the quiz with new board positions they hadn't seen before, but according to Alpha Zero, like the same vector. And they all were able to solve the puzzles now. They all learned the superhuman concept. And several of the chess masters were like, what an interesting day. I did learn something new about chess. And they try to articulate, I learned that it's important to develop queenside power and this and that, whatever, right? They have some whatever words that they tried to use to describe what they were doing. But like some new concept they had never seen before. And so then what the authors of the paper like to say is that one of the star participants that was most enthusiastic about the day went on 2 years later to become the chess champion of the world, still reigning champion today. Must have learned something that day. And so, but anyway, so that's the story of this. And I just wanted to show you what this research. I think it's pretty interesting. I don't have time to go over this other thing. Maybe have we talked about the function vectors paper in this class? We have, right? And so the exercise that we're going to do next Tuesday has to do with function vectors a little bit. So I mainly have you think of like a contrastive pair of prompts that you might want to patch between. It has to do with your research. And I think one of the things that we'll do is we'll try to pull apart the attention heads to try to patch the individual attention heads. I try to have you step through some of these things. Okay. All right, guys. Thanks a lot. See you.